Okay, let's final lecture for the class. And so really what this one is actually just more just kind of what's been going on, and I'll say in sort of recent advances. And I decided instead of making just a very long talk, just a little bit on high-speed imaging, because many of you probably are familiar with high-speed imaging and kind of what it's been able to do. And I'll just show you some work that we've been doing in my lab. So this is, again, more some updates on kind of, kind of a research talk more than educational material. Okay, so this is high-speed imaging in 1887. And so this is Edvard Muybridge. And this was sort of one of the first examples of utilization of high-speed imaging. And so actually what this is, many of you, I don't know if any of you are familiar with the quote-unquote Stanford horse, but this was a field that was, I think when you get to here, you have like 16, it's set up in kind of a linear array of all these different tripwires, okay? And every time the horse hit one of these, it took a still photograph. And the reason this was done is I kind of use this as an example, is that around this time, there was actually a debate on when people painted horses, whether or not their legs were out or whether they were in. And this was actually not known. You just didn't have it, you can't see it in real time. And so there was property given along Stanford who commissioned this work to be done so that they could draw, so that they could actually see what's happening. And they learned that all four legs are off the ground at the same time, and they're actually in an inward position and when they're in their highest point. And so, again, as combustion scientists, we have no real interest in galloping horses, but this is actually a very nice example of a diagnostic, if you will, in terms of high-speed imaging that had a particular question in mind, okay? So I'm not going to talk about, again, a lot of these images are getting a bit old now, as you can imagine. I put these slides together over the years. I'm not going to really talk about what you can do with, say, commercial high repetition rate laser systems. Many of you in your labs will have what's from diode pump solid state systems, high-speed lasers, high-speed dye lasers, and you would have either read papers or seen people who do high-speed OH imaging to look at kind of dynamics. I keep these in my slides even though they're now heading toward a decade because they were some of the first, and they're really nice ones and they're challenging environments. Swirl stabilized flame doing simultaneous high-speed PIV and OH PLIF to look at the interaction between the velocity and field and the flame front, and work at Michigan done by Brian Peterson and Volker Seek looking at high-speed fuel concentration and its interaction with the velocity field. So again, these are sort of, the laser system has gotten a little more powerful, they can go a little bit faster, cameras gotten a little better, but they kind of give you kind of a general idea of what can be done. What I want to show is what we've kind of done in my lab we started this about a decade ago and built one of the more energetic systems, and I'll take you a little bit through this on what we did on something called a pulse burst concept. Okay, so this is different than buying a commercial system. Although I say that you actually can buy pulse burst systems commercially now. You have been able for a few years. There are some differences, but again, this is now a commercial technology, so I need to sort of remove that from my language. So the way that a pulse burst concept works is a little bit different. Let's imagine you have some series of pulses. Let's say you either have a laser, just a high-speed laser, but it can be very weak, right? It can be nanojoules, if you will, or microjoules. It doesn't have to be high-powered. Or I just flip this laser pointer over and over really fast, right? So, and that's what you do when you take a CW laser and slice it with dual Pockle cells, okay? But bottom line is I create a series of low energy beams that are operating continuously. Then if I feed them through a gain source where this gain source is only on for a certain amount of time, I can end up with a burst, if you will, of high energy pulses, right? So I've added gain. And the reason I do that is I can ultimately, the whole idea is to amplify this limited envelope of pulses to very high energies such that they still don't pass the kind of the thermal damage threshold of the laser gain medium, okay? So what I mean by that, commercial solid-state diode pump lasers, all those are always going to be limited by the amount of energy you can get out because just thermal considerations, right? If you have a 10 kilohertz system operating at a few millijoules, you're generating a tremendous amount of wattage, right? And the laser rod will eventually go kablooey, right? But if you have extremely high energies, but only over relatively small duty cycle, the time average power of a system like this is still pretty low. And so what I'm going to show you is a system where we can make measurements at 10 kilohertz with joules of laser energy. Same thing as you get at 10 hertz, but then the burst duration will only be tens of milliseconds. But still, for turbulence measurements, this is still a pretty long time, okay? So here's a photograph of laser in my lab. This is a custom system. I won't go through the of each stage, but what we did, we built this system is where we start with a very low microjoules per pulse laser system. So this is just now a fiber optic laser. And then it's just amplifying in a series of flash lamp pump amplifiers. It just goes on and over till you actually end up taking something that's going from microjoule level to we end up with more than 3 joules per pulse in the IR at 10 kilohertz, okay? And so if you think about that joule, that's about the same level of energy you get in a commercial Q-switch YAG, okay, at 10 hertz, okay? The burst duration is 25 milliseconds, so if you think about this in terms of what you can measure, it's like 250 consecutive images at 10 kilohertz or 2,500 at 100 kilohertz. With proper frequency doubling, now 4 years ago, we can do about a joule per pulse per leg at 532. So what this does is open up the possibilities of doing high-speed Rayleigh scattering measurements, high-speed Raman scattering measurements, these diagnostics that require a lot of laser energy that you can't do with, say, a commercial laser system. So here are some examples from several years ago. This is a non-reacting experiment where it's propane into air, and we're looking using, again, our mixture formulation, where we're looking at the mixture between the fuel jet and the ambient to determine molecular mixing and just non-reacting jets. Here's where Rayleigh scattering was utilized in the DLR flames to measure high-speed temperature images. Okay, and so again, we make measurements. Both of these go upwards of 25 milliseconds of data, although we cut the movies off because you just wrap them around and save memory in the computer. But what we could do with these, we had worked hard just as much on the laser systems on the optical collection, and we could ultimately get into very high signal and noise in a lot of these measurements. No intensified cameras, nothing, just all CMOS cameras so that we could have high resolution and high signal noise. So here's just an examples to kind of look at just turbulence. They're beautiful images to look at, I think. So if we just look at a single point, you can actually get the time resolved fluctuations, the same as you would get from a probe measurement, say like a hot wire or a measurement, but now you get it for the full 2-dimension. And then we can resolve all the turbulent structure. Okay? And again, kind of really interesting images from a turbulent flame. The reason, one of the advantages of sort of high-speed information is that we can look at cause and effect, especially if you can ultimately combine these with flow field diagnostics as well. Here's a nice, healthy, high-temperature region. It's most likely a high-temperature reaction zone that shows it's just being segment shredded away, but then ultimately it reheals itself in just 100 microseconds. Now, this just may be out of plane motion, or it may be extinction, but it shows you the vast range of dynamics that occurs in even these simple laboratory-type flames. Okay? Again, like I said, because it's high speed, because it's high energy, we could do measurements similar to what's done at Sandia National Labs for high-speed spontaneous Raman and Rayleigh measurements. And here's an example. These are, if you look at what these are, each one of these is a radial measurement from a jet flame, and then they're stacked in time. So after all the calibration, all the procedure, here's temperature, the fuel hydrogen, oxygen, water, and then the mixture fraction. And then this is just looking at them as a function of time. So you can see all the fluctuations in time of the different major species. And this was them put into a mixture fragment coordinate system. So the reason we do this is that now you can look at just over a single 15 millisecond burst, the amount of fluctuation in mixture composition that you can have in a turbulent flame, okay? So you have extreme variations. We're covering the entire state space here in terms of, this is temperature and these are all the species. And not only we're covering the entire state space, you can see the large fluctuations from near equilibrium conditions, okay? So it just kind of characterizes the large amount of mixing fluctuations that exist in these type of flames. Well, an application that we've spent some time doing with these are auto-ignition experiments. In my group, we look at a lot of transient processes as well. Many of you I've heard, after talking with you over the week, a lot of you look in engines and these type of environments. And again, you'll know then that auto-ignition of fuel injection obviously is an extremely important environment, process, a number of environments. Diesel is where it always comes to mind. You have compression ignition, you squirt fuel in, it ignites. It also is important in scramjets, especially for relight applications. You want to prevent auto-ignition in spark ignition and in ducts of gas turbines because they can lead to catastrophic failure of components. It's a really cool problem. That's why we have several projects in auto-ignition. I really like the project because it's a coupling of fluid turbulence, reactant mixing, and finite rate kinetics. And they all have very similar timescales. So the turbulence and the kinetics have very similar timescales. So not only is this a practical problem, but it's one, I think, of academic interest. So this is one I use kind of as a motivation slide. This is from Christoph Arndt at DLR. And they did some measurements in just a pulse transient jet results like I'll show you. And what they found, just taking simple chemiluminescence measurements and then looking at the statistics of the ignition time versus the ignition height, found that the ignition seemed to be fairly repeatable temporally, but very spatially intermittent, okay? And they hypothesized in a set of papers that it's most likely due to, or it could be due to mixing fluctuations or scalar dissipation rate. Remember, scalar dissipation rate is the rate of mixing, okay? So the rate at which mixing fluctuations are destroyed. And so we set off with them in a collaboration with our first, it was to look at these mixing problems. So here was the experiment. The pulse burst comes in, laser comes in. We have a series of Rayleigh scattering camera, a sheet correction camera. So we're looking at this, our beam sheet intensity profile in just a uniform air. We're looking at chemiluminescence, slightly off axis, but then we correct it, and then down along the laser sheet. So here's just an image of the setup. You can see all the scattering from the dust particles in the air, but then you have this nice filtered air, and then the high temperature co-flow. So what I'm going to do is show a video that very similar type experiment. This is a newer burner that we have, but it demonstrates the process, much larger burner. Really what it is, if you look back, all of those, we just fire pulses of fuel at about 10 hertz. Each one of these are now slowed down, and each one of those events from fuel issuing all the way to ignition is a single ignition event, okay? This is going on at 10 hertz, but we've slowed it down. And we do time-resolved measurements from fuel injection all the way up to ignition to try to characterize the mixing field before ignition, okay? So it's a transient experiment, okay? Here's an example of the mixing field from this DLR version, again much smaller version than this. This DLR version where we see the mixture fraction field, again, the state of mixing between the fuel and the high temperature air. Keep in mind, this is fuel issuing into about 1300 degree products. So the co-flow are the products of a lean premixed hydrogen air flame, okay? And so that creates your oxidizer. It has about 10% O2 and the rest combustion products, very high temperature. And then we pulse fuel into that system and then watch it ignite. And so just from this injection sequence, you can see very high fidelity measurement. They're wonderful quality of looking at this transient impulsively started jet issuing into this high temperature environment. Again, good repeatability on the injection characteristics so that we can actually start looking at this in terms of statistics. Again, this is a methodology on how we use Rayleigh scattering to get both temperature and the mixing characteristics. We remember we did this in our lecture 11 where we said that if we just have a binary or two-stream problem, which before ignition this is a two-stream problem, we can write our equation this way, which allows us to solve for the fuel mole fraction, but also by knowing, looking at the different heat capacities between the oxygen and the fuel, you actually can write another equation for the fuel just as a function of the heat capacities, and then through an iterative solution, you can actually get two variables from one measurement. Okay, so it's valid from fuel injection through ignition. Okay. So here's a movie, Rayleigh scattering, that then they've been reduced into the mixture fraction field and the temperature field. And I'll let it play through a couple times along with the simultaneous OH. So initially we have cold injection, no ignition, and then after a certain amount of time, the flame ignites. So again, we're monitoring the mixing field and the temperature field both before and then during ignition, okay? And our goal is, what was that mixing field? What was the temperature field? What was the rate of mixing before ignition? So this is just an example of a sequence. Again, it shows that the ignition is occurring in this kind of cusp, okay? Other questions we wanted to answer is, okay, when is ignition? Is it occurring during a transient process, during a steady state process? So we look at kind of the average mixer fraction profiles as a function of time. Okay, and so if we look at the average of these injection profiles for 0.5 milliseconds after injection, 1.5, what you can start to see is that steady state of the impulsive started jet occurs about 1.5 milliseconds. Okay, we get self-similar jet profiles at that point. So that means steady state, it's the same at that point after 1.5 milliseconds. It's the same as we're just running the jet continuously. Okay? And so what we were interested in is knowing that when this jet achieves steady state, that's on each, that's the time after injection that it achieves steady state, so on each pulse cycle. So now we wanted to look a little bit at the statistics of the injection time and height. So what we did is we looked at the original kernel formation, and then the centroid of the original kernel would be the height, and the time would be the ignition delay time under turbulent conditions. And you compute the PDFs, and really what you get to is the fact that if you look at this, the most probable time, the mode of the PDF is around 2.5 milliseconds, and even down at the tail, you're only at about 2. So since we're achieving steady state profiles at 1.5 milliseconds, the actual injection is occurring when the jet is operating in steady state. Now, this is a nice feature that it's not occurring, at least for these are atmospheric conditions, and this is important for numerical modeling because there may be a way to sort of take an easier way out instead of determining kind of a full transient fuel injection. If you're just interested in injection, you may be able to model this as a steady state with activation chemistry with some sort of predetermined induction time. Again, this was just an outcome of one study, but clearly a tremendous amount of work is needed to understand these time scales. Okay? Now, where is it igniting and what is sort of the physical mechanism of that? If you look, we took our mixture fraction fields, took the gradient and squared, which is the scalar dissipation. So that, again, that's the rate of mixing. That's the highest bright layers are where you have high levels of mixing. Black is no levels of mixing. The blue is the stoichiometric contour, okay, the primary reaction zone. And the red is now that ignition kernel, except we identify it this time as about 50 K above co-flow temperature to signify ignition. And what we can see here is that the ignition is occurring in these cusps. Okay, we do this statistically too. It's occurring in very low scalar dissipation rate and very lean regions. So what we find, and this is dependent on fuel, so let me point out, but for these simpler hydrocarbons, ignition is occurring in very lean regions and very low scalar dissipation rate. It's essentially trying to stay away from turbulence. That's kind of the answer. And we see this, and this is DME, and we see this for methane as well. So really you have kind of a competing set of conditions for these certain experiments. You have hot co-flow outside, right? So we know kinetics scales with temperature, very non-linearly, right? Exponentially with temperature. But it's completely unflammable. You have mixture fraction of 0 in the co-flow. So what you're doing is ignition is occurring where you're moving in far enough where you're becoming just flammable enough, but you're still hot. It's a competition between the temperature, keeping high temperatures, and being flammable, okay? Now, is this necessarily assured for all fuels? And no, actually it's most likely not. Ignition usually occurs rich for things like heptane, and it has to do with something called the most reactive mixture fraction, which is where ignition is likely to occur. But for these type of conditions, these simpler systems, these were the first experimental results that confirmed some DNS calculations that showed it would occur on these very lean conditions under low scalar dissipation rate. These are just more joint probability. That's just showing, hey, where's it igniting? And again, it's shoved down here in this corner. Very lean and very low levels of scalar dissipation rate. Okay, and so the majority of the kernels occur at very lean conditions. And you do get a few samples that'll pop out here. So, and so they're likely most likely they were close to something that was decaying. But again, we can kind of show this statistically as well, that the most probable conditions are very lean because they're hot and very low levels of scalar dissipation rate. So ignition is really wanting to occur with very little turbulence. Okay? So that's all I really wanted to show, like on that. And the last thing, just a couple slides, this is going in, I just wanted to kind of, the main reason I'm doing this is pique your interest. And like I said, it's going through your grad school. Think outside the box and do some of these harder type things. Do these things where I want to look at some very interesting questions. So here's something that was done at Sandia right before Rob Barlow's, they kind of shut down operations there. This was a method to actually collaboration between Sandia and Darmstadt to measure heat release. I think we talked about this several days ago when we were doing PLIF, is to say there's a method, I think I let it off the bullet point that said heat release is, really people want to see heat release and reaction rate, but it's extremely hard to measure, right? And so there's the visualization technique where you look at one species and one species, their overlap gives you kind of a visualization of the heat release, right? But what about if we could make quantitative measurements? So what they did is they said, okay, when you have a Raman measurement, you have all of these major species, and you can easily add a LIF measurement with it. Let's say you do something numerically beforehand that you take a 0 degree, like let's call it a well-stirred reactor, just a model, a chemical thing, but you constrain the measurement such that it sticks with whatever your major species, whatever you measured. You essentially bound the solution where it can't deviate from that, and then it goes through, you get an approximation of the full chemical state. Because what happens is if you run a 0 degree bath gas, you put in your fuel, your oxidizer, the appropriate temperature, and then as it starts to evolve, you don't let the major species and OH change beyond what you measured. It's going to give you solutions for all of these other species that you couldn't measure that are, at least based on your kinetic model, that are associated with your measurement. So you get what's called an approximated full state, as if in some ways you were to measure these. Okay, now again, it's not exactly accurate, but it's a really good idea. So some of the different methods that they did with this is they allowed these major species fractions to evolve within the bounds of uncertainty, or you keep them fixed as they evolve to a steady state. You add OH. These are all details in a couple of, they just tried different options. So as a way to test this, they took DNS data. We like DNS. Remember, we have DNS, we have truth, right? So let's say we treat DNS as real data. We treat this as experimental data. You only take the major species that you can measure via Raman, okay, from the DNS. Use that You bend stuff such that you get the same resolution that you have experimentally. And so again, you're using the temperature and the major species from the DNS as input, and then you put it through this methodology, and then you start to look at, this is something called a chemical mode, but we're not going to worry about that, chemical explosion mode. But here's your heat release rate from this approximation method to those from the full DNS. Truth versus this kind of approximation method. And so if we look at this, what I'll just kind of take your eyes to is the fully resolved would be the actual truth. That's the DNS. And then the approximate OH is this method, as if you were to have the major species from Raman scattering plus an OH LIF measurement. You can see the red is truth, and this green, okay, is a really good, almost quantitative proxy, or almost a quantitative measurement for the actual real heat release. So this method has a tremendous amount of promise, right? And so this is really exciting, and so I hope they do continue to push this. But I bring this up because this is, although this was not done by, well, actually a lot of the analysis was done by a grad student, this was thinking a little bit outside of the box. I mean, Raman scattering measurements have been done for 20 years in Rob's lab, right? And only recently did someone have the idea, like, okay, what if we try this? And by making, having a reasonable hypothesis, having just a reasonable thought process, I think they're going to be able to develop a kind of a tool and a diagnostic that we've really been searching for multiple decades. And so, again, we've tried to do that in my group. I try to encourage my students and my postdocs to do this as well. You know, if there's a problem such as resolution and PIV, we've attempted to tackle this with a certain problem. And it's really, so this kind of leads into a lot of, you know, kind of my final thoughts is I don't have any more technical information for you. What I have is that don't be confined by what just exists in the literature, whether we're talking about from a diagnostic, an analysis, a measurement, or the experiment. Think outside the box. That's kind of a cliche, but truly think, okay, if I have a problem, if I have a physical problem I want to look at, maybe there are certain things I have to do. Instead of saying all the time, okay, I have this problem, what can I use? Say, what should I use? You know, and then develop in that context. And so my final words are, again, thank you for your attention. It really is appreciated. You guys can bear through all of these weeks. I'm sorry, all these hours in this 1 week. It seemed like weeks, right? This actually is half a semester in a university. We have 15 hours. That's about half a semester, 15 lecture hours. Okay? So you guys in a week basically got about half a semester's worth of material. Keep your enthusiasm. I've been extremely impressed. Again, I know you like what you're doing, so keep your enthusiasm. That's what will keep you finishing and moving beyond. Hopefully you can see I still enjoy what I do after these years, so I've tried to keep it. Now, a couple of things, just my kind of advice. Understand how your measurement techniques work. Hopefully that's why you sat in this class, to kind of pull the curtain back a little bit. Don't blindly apply them. And my favorite one, it's okay if you have error and uncertainty. Please report it. Not all measurements are great, and not all measurements have 10% uncertainty, as every single measurement seems to have in every paper. Every measurement has less than 10%. They don't all have that. So, and last thing, if you have any questions, feel free to contact me. Again, I don't have to worry about my email getting out there. It's on the web anyway, so you know. So I'll do my best to answer. At least I'll refer you to a suitable source. And again, so I thank you, and that's it. I'll take any questions about anything in the course if you guys like to ask it. Anything? Yeah. Yeah.
Yeah. Do you have any input on
like measurements and what exactly, whether it's the dispersed phase or the continuous, liquid or gas phase?
The gas phase.
Okay, and types of things you're looking at, mixing measurements, velocity, temperature, I mean, are there certain things?
Like ignition.
Oh, so some of the measurements, if you're downstream of the liquid core, a lot of the same diagnostics that I just showed here actually can be applied. So Rayleigh type scattering measurements if you're not being interfered with the droplets, the dispersed phase, and you're not getting interference from your windows. That's actually what Lyle Pickett at Sandia, if you're familiar with his work in high pressure systems, has done for many years. Use Rayleigh scattering, look at the mixing that occurs before ignition. If you actually want to look at sort of the kernels as they evolve, even optical chemiluminescence is good, and then any of the PLIF techniques, the things like formaldehyde will give you kind of lower temperature chemistry, especially if you're high pressure now. That would be your first stage ignition, right? And you typically then have a negative temperature coefficient. And then your second stage, high temperature, would be things like OH PLIF and things like that would give you kind of the high temperature gases. But there's a whole gambit. It just really depends on the question you want. Now, when you have questions about the liquid phase, things become a lot more complicated. Those measurements are much more difficult. Did that give you a little bit of insight on? Yeah. Okay. Other questions? No? All right, well, thank you.